How's everyone doing?
It's Friday.
It is Friday, so I'm in favor of covering what we need to cover and then heading on to a weekend. Here, 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 however it goes. Anyway, any questions before we get started? All right. Now, before we do a bit more 2D vector stuff, I actually want to show you something from the homework first. I do welcome and encourage students to ask homework-related questions during class, because odds are someone else has the same question, and if I can explain it all at once, then everyone gets the information. Real quick, I want to quickly look at, this is chapter 1 and 2, question number 9 on the homework. And this one puts some numbers to the proverbial tortoise and hare situation. We're given the speed that a tortoise can run, and you're told that a hare can run 20 times that speed. And something to note, if you've been working on the homework, is that all the numbers that you see in red are slightly randomized. So any red number is going to be unique to your version of things when you load up the assignment. I encourage classmates to work together. You can work with each other outside of normal meeting hours, and you can also work together at the study sessions that the physics department holds on Tuesdays and Thursdays. It just means that if you are working together, you have to determine the method, and then everyone plugs their numbers into the method, and you can't just copy the answers directly from somebody. But teamwork is still good. The methods are the same across all of them, just slightly different final answers. It also means that if whatever I'm about to show you, you'll have to change all the numbers in red before you do it for yourself. Now, whatever your exact version of the question is, you are told the speed a tortoise can run, and therefore the speed the hare can run, which is just 20 times whatever number you're given. And you're asked to figure out the time the race takes and the length of the track. And the issue that students encounter when doing this is that you're given the speeds of the two animals, but if you then try to figure out the distance they run or the time it took them, you don't actually have any other parts of either of the formulas for either animal. You don't know the distance the tortoise or the hare ran, and you don't know the time the tortoise or the hare ran. And so, if this is where you begin your work, you quickly arrive at a situation where you have two different equations with two different unknowns apiece in them. So 2 equations and 4 things that you don't know. This by itself is unworkable. Because if you even just have one equation where you don't know all but one piece, then you can't do it. You can't find a single answer out of that. So if this is where you leave it, you're just done. You can't go any further. But there is a trick that I want to teach you, and I'll talk about it now because it's something we're going to do periodically in here. It's a trick I call 2 equations, 2 unknowns. We may not know exactly how far each animal ran or the time they ran it in, but we do have information about the relationship between the distances ran and the times it took. Because the question does specify they start at the same time, but the hare then falls asleep for some amount of time, meaning that if the tortoise is running for the entire race, the hare runs the race in the tortoise's time minus the time it was asleep. So, as an example, if the tortoise is asleep for a minute, and if the hare is asleep for a minute, and it takes the tortoise 1 minute and 3 seconds, it took the hare 3 seconds to run the whole track, because it was only running for the time it's awake. And that relationship means I can rewrite the hare's velocity equation to be in terms of the tortoise's running time. Rather than using time hare, I can use time tort I just shortened it to tort for my work here. With the caveat that however long the tortoise runs, it takes the hare, some number of seconds less to run the whole distance because it was asleep for that time. So that doesn't really factor into the tortoise's speed. So instead of t hare, I've got t tort minus the number of seconds the hare was asleep for. Mine says 1 minute, so you have to convert from minutes to seconds before you can use the number. And we can do the same thing to the distance that the hare runs, because it specifies that the tortoise wins the race, so the tortoise is going to run the entire length of the track, and that the hare almost catches up. It says that the hare loses by the length of the tortoise's shell. So to try to represent that visually, the tortoise runs the full racetrack, and the hare, this is not to scale, the hare makes it in a very short number of seconds up to the tortoise's tail, whereas the tortoise at that point, its nose had crossed over the line. So they run almost the same distance, but not quite the same distance. And you're told how long the tortoise is. It gives you a number for that. I've got 20 centimeters. Note, when you're doing this yourself, do note how long your tortoise is. How long your tortoise is. That's a weird pun. And you can use this information to, like we rewrote at the time, rewrite the distance the hare runs to be in terms of the distance the tortoise runs. So instead of delta x hare, I've rewritten it as delta x tort minus the length of the tortoise. It tells us the same information, but I'm rewriting what variable it is in terms of. And that means I've changed the formula to be the hare's velocity is equal to the tortoise's distance minus the length of the tortoise divided by the time the tortoise took minus the time the hare is asleep. And this has transformed this equation from involving completely separate unknowns from the tortoise to involving the same unknowns as the tortoise. So now we have two different equations with the same two unknowns in them apiece. That's why I call this situation two equations, two unknowns. They have the same two unknowns across both of them. And when you're in a situation like that, you can use the two equations together at the same time to sidestep the fact that you don't know either unknown by itself. To elaborate, I'm going to leave this up on the board so you can copy it down and use it for your own work. I'm going to take this first equation and rewrite it in the form of one of those two unknowns. So here I'm taking 0.15 equals x tort over t tort and rewriting it just as x tort equals 0.15 times t tort. So same equation, just rearranged. And this means that wherever you see x tort in any of your work, you could write this instead. The tort's velocity times the time the tortoise is running. Anytime you see x tort, you can write this instead because they're equivalent. And that means you can write this into the hare's formula in place of the x tort we've added there. So down here, I've taken this equation, 3 equals the hare's information in terms of the tortoise's information, and I've written in 0.15 times t tort instead of the x tort that's normally there. And upon making that substitution, you've eliminated one of the unknowns. Now it's just the same unknown twice. T tort is now here in 2 positions. This has changed it from being impossible to, what was the word I used before? Weird but possible. Impossible, weird but possible. Because now it's the same unknown in 2 positions. And you can use algebra to eventually turn this into time toward equals number. So by doing this trick, you can actually finally get a number for the time the tortoise is running. And because the tortoise is running the whole time, the tortoise's time is this answer. That's why I set it up this way. So doing this, solve for t-tort, you will get the right number here. You input it, you make sure it's correct. There's no penalty to leaving like B blank as you check your answer to A. You can check each part separately. So input your answer to A, make sure it's right. Once you know it's right, you can then take your tortoise time and pop it back into either of your previous equations to find the distance the tortoise ran, which again is the length of the entire track since the tortoise covered the whole distance. How's this feel? As a general method for skirting around times when you don't know multiple things. Cool. This tactic won't be super frequent. It's not going to be like something we deal with every single day, but it will come up. It will come up from time to time. So when I say two equations, two unknowns, this is the method I'm referring to. Questions? Concerns? All right. Once again, any homework questions at all, at any time, please ask me them. I want to know, and then I can help everybody all at once. It is okay if you even have them in the middle of a lecture. I will waylay what I was planning to help you understand physics, because that is literally my job. So, if there's nothing else on your minds at the moment, then I plan to continue practicing a little bit more 2D motion and vector addition before we call it for the weekend. This will kind of bookmark the end of chapter 3, and the next week we're going to be in chapter 4, studying forces and Newton's laws. Force is a new vector, and since it's a vector, we're going to be doing this to it. So I want to make sure this makes sense before I go adding a new vector onto things. So here we have two vectors that need added together. You can consider this to be like two different parts of a hiking trip. Walking 20 meters in this direction, stop, turn, and then walk 40 meters in this direction. And the goal is to figure out where you wind up at the end of this. What is the vector that describes your final position in relationship to your starting position? To do that, we can add the two vectors together, vector addition. But are we legally allowed to just add 40 to 20 and call it a day? No. They don't point in the same direction. They're both in weird mixed axes. So before we can add them normally, we have to break them down into their components to add x to x and y to y. On Wednesday, this is a little more straightforward because the vectors I gave you for that football player or entirely in either axis. But here, they're mixed on angles, and we have to split them up first. So, I've labeled them as the red line, vector 1, and the blue line is vector 2. So we need to find x1 and y1, the legs for vector 1, and x2 and y2, the legs for vector 2. Whenever you have a vector like this, you can always turn it into a right triangle. I just tend to start at the slanted line and kind of unfold the vectors down and out from it. There's a couple different ways you could draw it if you wanted to, but I like this way. It keeps the triangles from overlapping too much. And at this stage, we would like to consult SOHCAHTOA and figure out what those legs are. So, questions now before I continue. All right. In order to use SOHCAHTOA for each of these angles, we first have to redefine what opposite and adjacent are from our current perspective. So looking at this 40 degrees, what leg is the opposite leg?
y1.
Very good. And by process of elimination, that's going to leave x1 as adjacent, and the 20 will be our hypotenuse since it's the slanted one. So, to start with, which of these three terms isn't going to be useful to us yet?
Tangent.
Tangent. Tangent's not going to help us yet, because it says tangent equals opposite over adjacent, which would end up looking like this. So, one equation, two unknowns, not helpful yet. So, for this one, I'm going to recommend sine and cosine. Tangent is only good if the hypotenuse is the one you don't know. So sine of our angle is going to be opposite over hypotenuse. Our known angle here is 40. The opposite leg is y1. Handwriting is not great today. And the hypotenuse is our 20. To get the x leg, I'm going to recommend cosine. K is adjacent over hypotenuse, so x1 over 20. And that will tell us the legs of this particular triangle. I'd like you guys to work these as well, so that one, when you get the numbers, please tell me what they are. Two, we'll use this to check and make sure your calculators are all in the correct mode.
I already multiplied each side by 20, so 20 times sine of 40 is 12.8557.
Fantastic. I'm just going to round that to 12.9 for simplicity's sake. And what would x be?
.3.
Excellent. Any issues arriving at these numbers? All right. Now, since these are vectors, I do like to note direction as I write these down. The original vector points up and up and right. So the y leg points up and the x leg points right. Questions or issues determining these? All right. We'll do the same thing for the other one. I like to color code my work when I can. I don't have a blue marker, so I'm going to use green. We should check opposite and adjacent for this one too. And it's like the triangle's not an exact match, but it is at least oriented the same if mirrored. So for this one, x should also still be adjacent and y should still be opposite. That is not always true though. In this particular case, it'll be the same structure for each, just plugging in different numbers. So same formulas arranged the same way, but using 40 meters and 25 degrees instead of 20 meters and 40 degrees. But there will be times where sine does not give you y and cosine does not give you x. Because again, it depends on the perspective of the triangle you're looking at. If I instead drew one of them like this, opposite is actually x in that scenario, and y would be adjacent. So sometimes which one tells you what will flip. You always have to check the picture, always have to check the orientation of the information you have. So what do our legs turn out as for this triangle?
y2 equals 16.9.
Very good.
x2 equals 36.3.
Thanks. And since this original vector points up and left, its y leg points up, and its left leg, its x leg points left. So, divided everything up into our components. We are now good to be able to add the components like to like. Any questions or issues getting to this stage before that? All right. So, to do vector addition, I do recommend just literally adding them. So I'll just write out each of these vectors in component form, one over the other. We've got 15.3, comma, 12.9. And then for the blue one, 36.3, comma, 16.9. And to literally add them, add the x's to the x's and the y's to the y's, and we're good to go, right? I've actually left in a small trick. Can you spot it? The x legs point in different directions. The thing about your calculator is that it doesn't have a brain, which means as smart as the advertiser makes it seem, it's actually secretly really dumb. The calculator does not have the ability to look at this picture and draw context about the numbers you're feeding it, and therefore the numbers it gives you are also devoid of context. Your calculator doesn't know that the x leg of this triangle points in the opposite direction as this one. So it gave you out a positive number, even though technically speaking, one of those two legs needs to be negative to indicate that they are working against one another. Your calculator cannot tell you that on its own. That's a logic puzzle thing that we as beings with brains have to add into the situation from our own analysis, because we can see the picture, we are trying to interpret reality here. So you do have to think of these as reality-based logic puzzles rather than just math number crunching exercises. There will sometimes be cases where the gauging of how reality affects this has to be taken into account. Calculator can't give us that negative sign. If we never add a negative sign there, if you just continued from here, the answer you'd get would be 51.6, comma 29.8. And if we draw this vector out, it would look like this. But instead, the vector we're looking for looks like this, pointed up and left, and less left than it is up. Whereas this answer is way more right than it is up. That tells you something went wrong here. And again, what went wrong is your calculator didn't know that that leg points leftward. So that is a negative sign that we have to manually install ourselves, unfortunately. So if you're ever looking at the drawings and you think, hey, that doesn't make sense, follow that instinct. And if it's on a task, ask me about it. So adding in that negative sign will actually change this to 21, negative 21. And that makes more sense, because that's going to point left and up, more up than left. Final unit of meters. And that would be the coordinates of that last point there. So it would also therefore be the component form of the summation vector that points from start to finish. How do you feel arriving at that answer? All right. So that is one completely successful and finished way to describe the sum of these two vectors, but it's not the only way, and so we do want to practice the second one. I'm going to try to redraw the overall picture here without all the work over top of it. Red line for vector 1, green line for vector 2, and black line for the summation vector that we found here, where the x leg of that vector is 21, pointed left, and the y leg is 29.8. So, those are the components that form this straight line. That straight line kind of being the third leg of a larger triangle. It's not a right triangle, unfortunately, but we've sidestepped that issue. And we can use these two components to figure out what is the magnitude and direction form of that final summation vector. So kind of the opposite of how we started the question. We took two magnitudes and directions and turned them into components. Now we're going to turn two components into a magnitude and a direction. So we just want to reverse that process. How might you think to find the hypotenuse of that triangle that I've added there? Pythagorean theorem, very good. What is the hypotenuse of the Pythagorean theorem, A, B, or C?
C.
Very good. Negative 21 squared. Conveniently, I'm going to keep the negative that we got all the way through here to kind of show what happens to it if you do that. Thankfully, squaring the negative gets rid of it so that we don't mess up the rest of our work. So our hypotenuse should be the square root of negative 21 squared plus 29.8 squared. And if my memory serves, please tell me if I'm wrong, that should be about 36.3.
36.5.
Thank you. So that's the hypotenuse of our final summation triangle, and it would also be the third side of that weird knot triangle that all three vectors make. And we'd also like to know what direction that 36.5 points in. So how would you think to do that?
We gotta find theta.
Yeah, theta's the goal.
Yeah. So we use SOHCAHTOA as a sine of theta equals 29.8 over 36.5.
29.8. Yes, that will work just fine. I'll point out though, if that was not anyone's specific first instinct, since at this point we know all three sides, you could actually use any of the three SOHCAHTOA trig functions. I would usually pick tangent here, but you're correct. Since we found the hypotenuse already, sine also absolutely works. So I'll write out theta equals inverse sine of 29.8 over 36.5. And if I'm recollecting correctly, that should be approximately 55 degrees. Is that right? Cool. And that is the magnitude and direction of our final summation vector. How you guys feel? Now sometimes I will ask you for one form or the other, so you do have to be able to find both. And sometimes, like in this particular case, the process led us to one of them before the other. Any questions that are arriving at these answers or what they mean? Okay. Now I'm actually going to do the tangent version to demonstrate that it both works and also to kind of bring up an interesting point about this. And we're going to end today by studying, I'm getting ahead of myself. I'm going to show tangent. So if I wanted to use tangent instead, TOA is an opposite over adjacent. Yeah. So 29.8 over negative 21. I'm going to keep the negative all the way through here just to show you what happens. If you do it and it turns out weird, I want you to know why it's weird and what it means. Inverse tangent of 29.8 over negative 21 will still give you about 55 degrees. But doing it this way will interestingly give you negative 55 degrees. And you only get that negative answer if you're using the negative 21. So we didn't get it using sine because it just didn't use that leg. But cosine or tangent would give you negative 55 degrees if you kept the negative on there. And I want to address what that means. Because it doesn't mean it's wrong, and it doesn't mean you found some sort of weird anti-angle. This happened because, again, your calculator is real dumb. It only does what it's programmed to do. And it was programmed by mathematicians. And mathematicians have decided and enforced that if you're looking at a coordinate system, where left is positive x, up is positive y, and the negatives are informed from there, mathematicians have decided that all degree measurements are specifically meant to be tracked counterclockwise from positive x. This hopefully sounds familiar if you've had a geometry class before. And therefore, specifically, if your calculator gives you a positive angle, it's because, based on the numbers you fed it, your calculator thinks it is a counterclockwise angle. Whereas here, when we fed in this negative, it gave you a negative angle, meaning that your calculator thinks this angle is clockwise, which it actually is, based on the way that I drew this picture. So that's what the negative means. Negative means, based on the information you fed it, it thinks it's a clockwise angle. And again, sometimes its logic is flawed, because if you actually fed it a third quadrant angle, you give it a negative over a negative and you get a positive answer, which isn't always true if you look at it from the clockwise perspective. So your calculator is not perfect about this, but if it gives you a negative, it's because it thinks it's normal clockwise. Yes?
So we can obviously write it in the coordinate way. The other way where we write the distance at this degree angle.
Correct.
Would we use, since it's going to the second quadrant, would we use the negative angle if we were to write it at this angle?
That is a fantastic question. That segues into the next thing I wanted to talk about. Because whenever you're writing out this word answer for your final number, I'm just writing in something, then we'll talk about what it means. This here is a way to write out the magnitude and direction of our answer. We've got the magnitude here, and we're trying to talk about what direction it points in. So length at direction. And whenever you're writing this answer out, or optionally whenever you are reading someone else's answer or reading like a textbook question or a test question, the angle sometimes needs context for what it is in reference to. And that's the last thing I want to cover today, is talking about reference points for how angles are described so that when you see them, they make sense. So, based on the picture here, this angle that we found, I'm just going to call it 55 degrees, is clockwise from the negative x-axis. And that is not the way that mathematicians usually write all their angles. They start at positive x and tilt counterclockwise. So if all you wrote here was positive 55 degrees, a mathematician would read that and assume your answer looked like this.
Yeah.
Which it doesn't. Because they have created this system where, lacking all other specificity, angles start here and go counterclockwise. And since that doesn't fit our actual answer here, we have to add qualifiers to make sure whoever's reading it understands our intent. Now the qualifiers can be done rather straightforward, because if we look at our picture, we can see where I've drawn it here to where it starts on negative x axis and then tilts up. And honestly, the qualifying statement can just be as simple as that. We're looking at the picture, describing it, and then writing that description. So we can describe this as 55 degrees above negative x. Starting from the
So stay away from just traditionally keeping it on the positive x-axis and subtracting 180.
Well, you can do that. I kind of want to talk about the multiple ways this can be written. This is one of them. If you want to kind of just look at the picture as it is and not have to think about a larger coordinate system. Just interpreting the picture literally, this is a totally valid way to describe what's happening here. You start at positive x and then you tilt this many degrees physically upwards from it. But, as you pointed out, we can take advantage of a mathematician's normal reference frame, and you could instead write, hold on.
180 minus 54.9 is 125.1.
Thank you very much. And writing that by itself technically accomplishes the same thing. Because even though we've drawn it like that, 55 degrees from negative x, that would be the same as 125 degrees from positive x. And as long as it's counterclockwise from positive x, you technically don't need any other qualifying statements. So, if you were feeding it's Friday and sometimes I forget how to talk. If you were writing down this answer to give to someone completely devoid of context, and they had to make sure that they took this answer and drew the correct vector, and they were a mathematician, both of these are correct ways to describe it. So you always have to make sure to note the reference frame somehow. Questions thus far? Okay. The last thing I want to talk about is the fact that there is technically a third way, like a third reference frame you could use. Because lots of the questions in here, given that we're measuring reality, aren't going to necessarily specify that the vectors are positive x, positive y, et cetera, Sometimes they're going to use compass reference frame, north, south, east, west. Because we are trying to measure reality here, and in reality we do note direction using compass. So sometimes, frequently actually, homework and test questions are going to give in this answer, and WebAssign likewise would expect an answer from this reference frame. So rather than just in reference to the x and y axes, I want to talk about and show you how these things are described in compass terms as well. So here I have 4 random vectors, just direction, and I'm going to show you how they're written geometrically and also in terms of the compass. I guess cardinally would be the word. First, we have 30 degrees. How would you write this?
30, like 30 degrees.
Yeah, honestly, you can't just leave it at 30 degrees because it is counterclockwise from X. If you wanted to be specific,
30 degrees east, north of east.
hey, very good. You beat me to it. 30 degrees north of east. This means north of east, N of E. Sometimes it will write out the full word, sometimes it might not. So if you see N of E, or really any combination of the letters there, this would translate to starting at east and then tilting 30 degrees towards the north axis. The starting axis is actually the second one, and you tilt this many degrees towards the modifying axis. It's a bit weird that it's written in reverse like that, but it's a quirk of the English language. So, 30 degrees north of east. If it's ever direction of direction, this is what it's, the type of thing it's referring to. Because if you just tell someone northeast, northeast could be anything within this 90-degree wheel, within this 90-degree section here. So this is more specific than just saying northeast. Does that one feel okay? All right. Next, we've got 60 degrees from what?
60 degrees west of north.
Correct. Start north, tilt 60 degrees west. If I was to use another reference frame, you could also just say 60 degrees from positive y. All right, how about this one?
Due south.
Yeah, just south. South is fine. You could also say negative y. If you're feeling fancy, you could just call it 270 degrees, but I'm never going to hold you to that. And last one I've got up here.
That's just southeast.
Yeah, you could just call that straight southeast, I suppose.
But 45 degrees south of east.
Very good. South of east. You start east and tilt towards south. You always list the modifier that occurs next on your rotation. Say for this one here, it is true that by tilting away from north, you are becoming more south than you already were. But if you follow this along the path of the compass, you hit west before you hit south. So even though you are moving more down than you were, you list west because it's the next thing on the rotation. So some questions are going to use that system, since again, a lot of the physics questions look at it in terms of the real world. There's a few homework questions that involve planes flying in various directions, or a boat sailing in a specific direction in terms of north, south, east, west. So I wanted to make sure to address this system. We're going to practice it a lot. Every question that comes up, we're going to make sure it's very clear what direction it's pointing in when we're doing it in class together. How do you guys feel? Okay, no violent objections, it seems. That is actually everything from chapter 3 that I wanted to cover. And so, next week, we will begin learning about force and Newton's laws, which we don't have to memorize them or anything right now. I'm just going to show you them to set up next week. This is going to be the focal point. The next 2+ weeks. And I guarantee you've heard all of these before. I'm just going to help you make sense of them and make sense of what you already know. Questions before we break for the weekend? All right. Know if you're listening, and have a great weekend. if you guys are longer than I need to. I don't want to start lunch later than I need to. Oh, 126. If you're walking towards the bio building, it's the very last door on the right.
And are you gonna be able to?
Yes, I do Wednesday and Friday.